Hello, my name is Mike Shriver. I am an applications engineer in the Power Products Group at Linear Technology. Today, I will talk about the LTC3774 dual output step-down controller, which features sub-milliohm DCR sensing and is designed to work with DrMOS power stages. Here is an application circuit for a high-efficiency 1.2 volt 60 amp dual-phase converter. The inductor used is a 0.33 microhenry ferrite chosen for its low core losses and low DCR value of 0.32 milliohms. The PWM output of the LTC3774 drives the PWM input of the DrMOS device. The DrMOS itself consists of the gate driver, top MOSFET, and bottom MOSFET, all in a single QFN package. This high level of integration makes the solution more efficient and provides a smaller footprint. With LTC3774's current mode of control, more current can be provided by adding more phases. Up to 12 phase operation is possible. However, as more phases are added, MOSFET reliability becomes a greater concern for these reasons. First, MOSFETs are one of the part types prone to failure. Although MOSFET and DrMOS devices have excellent reliability, failures might occur due to a fault on the board or a defect in the device. Second, MOSFETs tend to fail short. And third, if any MOSFET fails, the entire rail or system may be brought down or the load may be damaged. The chances of a MOSFET failure occurring are very small, even for a 12-phase converter. But for cases requiring 100% uptime or where a costly processor or ASIC is used, a small likelihood of failure is not acceptable. Either the top FET or bottom FET can fail in a synchronous buck converter. If the top FET fails short, then large inrush current will flow into the fault. This current is due to the input voltage being shorted to ground each time the bottom FET turns on every switching cycle. Once the input voltage is pulled below the under voltage threshold of the converter will shut down and fault current will flow to the output where it will cause a momentary overvoltage. Afterwards, the output voltage will collapse. If the bottom FET fails short, then the input voltage will be pulled down by large inrush current flowing into the bottom FET short when the top FET turns on every switching cycle. Meanwhile, the output voltage will be discharged by the current flowing from the output voltage to the fault. To protect against MOSFET failures, a new concept was developed as shown in this block diagram of an LTC3774 90 amp 4-phase converter. Each phase is rated for 30 amps. If just one phase fails, then the other 3 phases will take over to provide the rated 90 amp load. Fault isolation will be provided by the hot swap circuit on the front end and the ideal diode on the output. Here is a close-up view of just one phase of this converter. An LTC4226-1 circuit protects the input. When either the top FET or bottom FET is shorted, a large inrush current will flow to the power stage. The LTC4226-1 hot swap circuit will first limit this fault current. After a programmed circuit breaker delay, the hot swap circuit will turn off the hot swap FET, then pull the fault pin low. The fault pin is tied to the HIZB pin of the LTC3774. When the HIZB pin goes low, the PWM output of the LTC3774 is floated, which in turn disables the DrMOS to prevent further switching. The LTC4352 ideal diode only permits current to flow from the local output to the main output. In the case of a bottom FET short, current flowing from the main output to the fault is blocked. Here is an example of a top FET failure. The failure was created by shorting the top FET of phase 1 with a resistance of about 2 milliohms. During the fault, the local input voltage for that phase collapses, but the main output has a small overshoot of 32 millivolts and undershoot of 40 millivolts. The LTC4226-1 hot swap circuit plays a large role in minimizing this disturbance by quickly and safely limiting the current flowing into the fault. After a few microseconds, it turns off the hot swap MOSFET and pulls the HIZB pin of the LTC3774 low, which floats its PWM output. This in turn disables the DrMOS. Due to the fast response of the hot swap circuit, phases 2 through 4 continue to switch even though phase 1 has a fault. Here is an example of a bottom FET failure. It was created by shorting the bottom FET of phase 1 with a resistance of 2 milliohms. The hot swap circuit quickly isolates the main input voltage from the fault. Even though phase 1 has a fault, phases 2 through 4 continue to switch. Further protection is provided by the LTC3774 disabling the DrMOS. After the fault occurs, the LTC4352 ideal diode circuit blocks the current flowing from the output to the fault. The ideal diode's quick response time allows for only a 19 millivolt dip in the output voltage. The LTC3774, when used in conjunction with hot swap and ideal diode circuits, provides a PolyPhase solution that is resistant to MOSFET failures. If the top FET or bottom FET is shorted, the converter survives and only a small disturbance occurs on the output. This and the fact that the LTC3774 is designed to operate with DrMOS devices makes it ideal for rails that require high output current, high efficiency, and high reliability. Please visit linear.com for more information. Thank you for watching.